Okay, I think we have enough to start now. Can everybody hear me? Thank you. Okay. Today we're going to be looking at blood vessels and um, and as other people come in, I'll just add them in here. Can everybody see the slide that says blood vessels and circulation? Hoping I'm sharing the screen yet. It tells me I'm sharing the screen, so I'm assuming I am. So, okay, thank you. Now, in So our human body has a circulatory system. It's a closed system. It's designed to transport blood around to the various tissues. We have a four-chambered pump, a heart, that pumps blood in two different circuits. One circuit goes to the lungs to get recharged. One circuit goes to the body. We call it the systemic circulation. And so we send, you know, low pressure blood to the lungs to become recharged with oxygen. We recover that blood coming back to the heart, and then we pump that out to the body under high pressure. So we have three different types of blood vessels that we're going to use. We have arteries, we have veins, we have capillaries. Now the arteries are the largest of the vessels. They're the strongest of the vessels, and an artery will always carry blood away from the heart. It doesn't have to be oxygenated. And when I say oxygenated, what I mean is that difference between 80% full of oxygen versus 100% full. Because we don't, the common term that you'll hear is deoxygenated blood. And that implies that the blood has no oxygen left in it. And that's not the case. The case is that there is about 80% left of oxygen left in the blood after it has passed through the body once. So arteries always carry blood away from the heart. They will either go to the lungs or they'll go to the body. Veins always bring blood back to the heart. They're bringing blood back either to the right atria where it's collected to get sent to the lungs, or the blood is returning from the lungs. Yeah, well, that's returning from the lungs to the left atria full of oxygen. So the veins always bring blood back, and veins are designed to bring the blood back under low pressure. Arteries are always going to be under some type of pressure, but they're going to be higher than the outside pressure. The pulmonary trunk, which leaves the right ventricle, will be about 20 millimeters of mercury. The aorta, which leaves the left ventricle, which is an artery, will be about 120 millimeters of mercury. So veins always carry blood back to the heart. Arteries always carry blood away from the heart. And the capillaries are right in the middle. The capillaries are essentially a one cell layer thick structure that carries blood to the tissues. And this is where all the work is getting done. This is where nutrient exchange takes place. This is where gas exchange takes place. This is where waste products are picked up from the tissues, because the capillary wall is only one cell layer thick. And so waste diffuse into the into the capillary from the tissues. And oxygen diffuses out of the capillary, from the red cell out of the capillary into the tissues. And CO2 goes the other way. So this is where, we have, this is where the work is being done. This is where the bulk of our blood vessels are located, are the capillaries. So they look very different. The artery and the vein are similar, as they both have the same three layers. The outer layer of an artery and a vein is connective tissue. The next inner layer is the smooth muscle layer. Both arteries and veins have smooth muscle, and that's determined. In the artery, it's used to constrict or relax the artery either to improve blood flow or to impair blood flow. And then it has an endothelial cell lining here. It says epithelial, which is correct. That's the type of cell it really is. But it's endothelial because it's internal. So we have this inner lining of both the artery and the vein with this non-stick surface. The capillary, on the other hand, is made up of a single layer of epithelial cells, usually simple squamous epithelial, or endothelial, if you will, and has a nucleus for each cell inside here. But the epithelial cell also makes up the lining of the lumen, the non-stick surface. So you can see that and the size comparison here is totally off. The size of the capillary is much, much smaller than either the artery or the vein. And you see below in the larger picture here, the artery has a much thicker muscular wall, this middle layer here, because here is the connective tissue layer on the outside. This is the smooth muscle layer around it, and then the epithelial layer is right surrounding the lumen. It has a very thick muscular wall because the artery is under a great deal of pressure. The pressure in an artery is 100 millimeters of mercury or more, whereas the pressure in a vein is somewhere between 0 and 10. So what we use the smooth muscle for in veins is to squeeze the blood back up to the heart. The artery here is designed to provide strength, with its muscle layer. We can constrict the muscle layer. We can narrow the muscle layer. We can raise pressure by constricting the muscle layer. We can relax the muscle layer, and the artery will expand. So there's all sorts of other reasons we have this difference in our muscle layers. So here's a illustration. The innermost layer is called the tunica intima, Latin for inner lining. Tunica means coat, made up of the endothelial cells that give us a non-stick surface. This is true on both arteries and veins. We have the tunica media, which is the middle layer, which is where the smooth muscle is located. And then we have tunica externa, which is where we have the connective tissue. Now, arteries and veins will start out from very large. An artery will be a very large structure, and it will continue to distribute itself to smaller and smaller arteries, leading to what we call an arteriole. That's what we're seeing down here. This structure here is an arteriole. It is a small artery, still has all the functions and properties of an artery, but it is a small artery, and an arteriole will lead into a capillary bed. That's what this network of small structures here that go from red to blue. That's a capillary bed. And our body is made up of millions of capillary beds with an arteriole feeding one end of the capillary bed, bringing in blood that's high in oxygen, high in nutrients, low in waste, and then giving up its oxygen, collecting waste products and collecting CO2 on the other side of the capillary bed, which then enters a small vein we call a venule. So you have an arteriole on one side and a venule on the other side. And then the venule will lead into larger and larger collecting veins to return the blood back to the heart. And one distinctive property that veins have that arteries don't is there are valves. This is a valve right here in the illustration for the vein. The valves are one-way valves that flip up. And so when to get the blood back to the heart, and we talked about this just briefly, I think it was yesterday, that to get blood back to the heart, the smooth muscle layers in the veins will constrict. The skeletal muscle around the veins will constrict, and they'll actually squeeze the vein and push blood up through these valves. These valves are located every so often in a vein. And as you push the blood up and you relax the pressure, the blood drops back down. But the valves are designed to go shut when blood lands on them. And so they close. So you squeeze blood up into a segment of the vein, and then you release the pressure, the blood drops back down, but it hits the valve goes shut. And so then we squeeze the next section. We're actually, this is described as milking the blood up to the heart. It's a slow process under very low pressure. So now our arteries, we got three different categories of arteries. We have the conducting arteries. These are the large ones. This is like the aorta, largest blood vessel in the body, coming right out of the heart under high pressure blood. These conducting arteries are very elastic. They have a lot of elastin embedded in with the muscle. And this is good because these arteries will surge as every time the heart contracts, a surge of blood will come into the artery, and the artery will expand on this surge. It will stretch out. And then as it moves forward, as that surge of blood continues to move through the artery, it will keep expanding as it goes along. But behind it, the area that was expanded will now contract. So we have the heart contracts, a surge of blood goes into an artery, the artery expands, another surge comes along, first surge of blood is moving forward, and the artery snaps back in position. This snapping back, every time there's a surge of blood passing through, it expands and then it contracts. That surge of blood is what causes the pulse. The pulse is a measurement of the contraction rate of the heart. And all it is the expanding and contracting of the elastic walls of these arteries. And they actually physically snap back, and we can feel it. We can feel it at the radial artery directly behind our thumb. We can feel it at the carotid arteries and the sinuses in our neck, where the carotid arteries separate and go internal and external. It's an area called the carotid sinus. It's direct. If you go straight down through the earlobes into your neck, you can feel your pulse there. And that's merely the snapping back of the carotid arteries as blood is surging up to the brain. After we get a little further out into the system, we start branching out off of these very large arteries. The aorta, everything branches off of the aorta. And the aorta will branch into the arteries that are named for the various organs that they're supplying, like renal artery we talked about yesterday. The renal artery comes off the abdominal aorta. Renal artery goes to each kidney on the left, one on the left, one on the right, bringing in blood under reasonably higher pressure, not as high as what's in the aorta coming out of the heart, but high enough to create pressure in the glomerulus so we can filter the blood. And we will send blood to the stomach, to the small intestine, to the large intestine, to the kidneys, to the liver, to the brain, the carotid arteries, for example, that go up, coming up also the aorta. They are a distributing artery, bringing blood to the brain. We have, so we're distributing our blood to the various organ systems around our body. Now, pressure is lower here, but it's still too high to be dumped directly into, to expose to tissues. So we have the arterioles. The arterioles are the smallest of the arteries, and they're going to lead into the capillary beds. Now, the arterioles are heavily innervated from the sympathetic nervous system. Sympathetic nervous system is going to control what we call vasodilation and vasoconstriction. Vasodilation is when a blood vessel enlarges, it dilates, it gets bigger. Like, you ever have your eyes dilated, at the optometrist, and they put those drops in there, and you can't see anything in bright light for about an hour or two or three or whatever. That's, the pupils have dilated, they've gotten larger. Well, the same principle applies here. The arterioles can dilate or constrict under control of the sympathetic nervous system. And this is how we move blood around in our bodies. For example, on a cold day, You go outside, it's cold. So your sympathetic nervous system will say, hey, we don't want to lose a lot of body heat. So we're going to restrict the arterioles that are supplying the capillary beds under the skin. And so they release what's known as norepinephrine, and because that's the neurotransmitter, one of the neurotransmitters used by the sympathetic nervous system. Remember, from AP1, they use epinephrine and norepinephrine. The parasympathetic side uses acetylcholine. But anyway, so we have the norepinephrine being released from the sympathetic nervous system. That causes certain capillaries, certain arterioles to constrict and reduce blood flow into their capillary beds. So you have less blood flowing in the capillary beds under the skin, and you are releasing less body heat to the outside on a cold day. On a hot day, we would increase we would allow those arterioles to dilate, increasing their blood flow, causing more heat to be transferred to the skin that we can then radiate away. And so we try to stay a little cooler. So the arterioles are the location where we do most of our vasoconstriction and vasodilation. When we go into a fight or flight response and we release epinephrine and norepinephrine to, particularly from the medulla of the adrenal glands, we're going to see an increase in heart rate and breathing rate and send blood to the muscles and to the lungs and to the brain. And we're going to ignore all the other systems for a little while. And what controls that is the epinephrine vasoconstricting some vessels, like to the digestive system, the reproductive system, the surface of the skin, the urinary system, which are right now in a fight or flight response not very important. So we restrict the flow to those systems, and we dilate the arterioles leading to the heart, lung, brains, and muscles, so we can respond. That's the whole thing of fight or flight, and that's where the arterioles come into play, thanks to the sympathetic nervous system. Okay, so the arteries are we have 3 categories of arteries. The probably most abundant category are the arterioles, and they're going to lead into the capillaries that form the capillary beds. Now, there are 3 types of capillaries. The most common type are what we see known as continuous capillaries. They're made up of epithelial cells held together with tight junctions, so they're rigidly attached to each other or vigorously attached to each other, but they still are leaky. Every blood vessel, every capillary is leaking. Plasma is going to be leaking out of these capillaries, but it just depends on how many openings there are here for plasma to leak out. They have gaps. We have to allow plasma to leak out. Plasma is going to be containing sodium, potassium, and hormones, and glucose. So all this material that's in the plasma will be oozing out of here. Now we're going to deliver a lot of glucose, to the cells, but we're going to be seeing, it's how we get it to the cells. We let it leak out of the capillaries. The only place where we don't have this leakage is in the brain, where we have the astrocytes. If you remember back to AP1, well, I say that a lot, don't I? The astrocytes wrap themselves around. Astrocytes are the most common type of glial cell, and the astrocytes wrap themselves around the capillaries to enhance the blood-brain barrier. The tight junctions and the astrocytes make it almost impossible for anything to leak out of the capillaries and the blood-brain barrier. But we depend on this leakage. This is what gives us our interstitial fluid, the fluid that surrounds the outside of our cells. The interstitial fluid, it allows us to transfer water back and forth with the tissues in our bodies. And this is where we maintain the sodium concentration outside the cell so we can have depolarization when we need it. So cells are high in potassium internally and low in sodium internally, but they're high in sodium out in the interstitial fluid. So that's how we can, and that sodium is coming from the plasma. The plasma gets recovered by our lymphatic system. We'll talk about that next week. The lymphatic system collects the plasma, and now it's called lymphatic fluid. And we filter that through our lymph nodes, and then we return it back to the plasma. Anyway, continuous capillaries, the most common type of capillary we have, they are still leaky. Fenestrated capillaries tend to show up in two places. These are the ones I was describing in lab yesterday. They look like a colander. They have lots of openings there, so they function like a sieve. The glomerulus in the kidney, in the renal corpuscle, the glomerulus and the Bowman's capsule make up the renal corpuscle. The capillaries have all these little tiny holes in there so that fluid can be forced out of the capillary in the glomerulus and start the process of filtration in the kidneys. What the kidney does is filter the plasma. The red cells and the white cells. We're not worried about the red cells and white cells. We don't want them in our urine. But we're worried what we're filtering is the plasma that contains all the waste products and also contains certain chemicals and nutrients that we want to keep, like glucose. We want to get our glucose back. So all of this is leaking out, is being forced out under pressure in the capillaries of the glomerulus, because the glomerulus is the capillary bed in each nephron. So we're pushing this plasma out. That's one of two places where we have fenestrated capillaries. The other location for a fenestrated capillary is lining the area underneath the small intestine. The small intestine is lined, 20 feet long. It's lined with simple columnar cells. Simple columnar cells, one cell layer thick, lots of mucus, obviously, because we want food products to pass through the small intestine. But directly underneath the columnar cells, the simple columnar cells, we're going to have this capillary network, so we can collect nutrients. Well, the capillaries there are also fenestrated. So we're using these capillaries here, these fenestrated capillaries, in the small intestine for absorption. So either filtering or absorption. We filter in the kidneys by passing plasma and any small molecules in the plasma through the capillary, the fenestrations, the openings. In the small intestine, we collect nutrients that are passing through the fenestrations into the capillary. So glucose and sodium and potassium and amino acids are going to be moving, into our blood supply through these fenestrations. They're going the other way. Instead of being filtered, they're being absorbed. So these are the two locations where we have these fenestrations. Now there's one more category, and these are even more unusual or more rare than the fenestrated ones. These are called the sinusoidals. These capillaries are very large, have very large openings in here. We usually find, and this is where we want to have the passage of lots of red cells. So we find, and lots of fluid. We find these in the liver. What's the liver do? The liver is going to clean up our blood. It's going to detoxify the material that the food that we've eaten, the liquids that we've consumed, go into our small intestine. They're absorbed through those fenestrated capillaries. The first stop they go is the liver to be cleaned up, to take out any toxic chemicals, to reduce the concentration of medicines, to take out coloring dyes, coloring agents in our food, to look for insecticides, things that we can destroy and break down. So this is what the liver does. The liver is it's like the pre-cleaning step, if you will, for our blood, because after the liver, then the food in the blood that's been processed goes straight to the heart to be sent out to the body. The kidneys, on the other hand, are busy filtering out the waste products that are formed. So we have two types of cleaning processes. The pre-cleaning in the liver to clean up what we've just eaten. You eat an apple and maybe you didn't wash it off and there's still some sort of insecticide residue on the skin. Well, your liver is designed to detoxify that. You drink an ounce of alcohol and your liver is designed to detoxify that. A toxicologist will tell you that everything is a poison. They like to say that the dose makes the poison. So even water can be a poison if we drink too much of it at one time. But the liver is cleaning up what we take in. And so we have these very large capillaries in here designed for the passage of lots of plasma with all sorts of nutrients and chemical additives, plus our red cells and our white cells. The spleen, which is going to be where red cells go to die, if you will, where we're going to break down old red cells and recover their iron and ship their globin out to be processed. They're going to have these sinusoidal capillaries. The bone marrow is full of these. Because what's the bone marrow doing? It's churning out all 7 types of formed elements. So we want to have a good passage of these formed elements into the capillary supply that's feeding the bone marrow. So these are, the sinusoidals are very large capillaries, very leaky capillaries. And we only see them in, like I said, in these 3 particular places. On the other, so at one end of the capillary, you have an arteriole supplying blood to the capillary bed. At the other end of the capillary bed, you have a veinule, a tiny little vein that is collecting the blood from all these capillaries. The veinules are also very leaky. Plasma leaks out into the tissues, and that's important. Plasma is always leaking out into the tissues, exposing the cells, and then being recovered by the lymphatic system, being dumped back into the plasma. So we're cycling it around all the time. We pass it through our lymph nodes in the lymphatic system, so the lymph nodes can watch if there's any kind of pathogen in our cells. The veinules allow much of this plasma to leak out. The veinules are also small enough that white cells can migrate through diapedesis out into the tissues, because after all, that's what white cells do. White cells tend to, they don't stay in circulation in the blood very long. They tend to go into the tissues when they discover a pathogen. Now they may discover a bacteria or a virus or an infected cell in the blood, but usually they're going to respond to damage to the tissue or a worn out cell or a bacteria that has invaded a cell or something like that. So their job is to leave the blood and through diapedesis and go out and hunt this thing down. So the veinules is where you'll see a lot of migration of the white cells into the blood. Just 1 or 2 layers of smooth muscle, not like we have in the arteries. Now veinules then come together. Veinules come together to form larger veins. The veinules will veins will have very low pressure, somewhere within the neighborhood of between 0 millimeters of mercury and 10 millimeters of mercury. This is much, much lower than the arteries or the arterioles. Remember, an artery starts out, your heart contracts and pumps blood into the aorta, and in a healthy individual, your pressure there might be 100 to 120 millimeters of mercury. By the time you get to the arterioles, your pressure is probably in the 30, 40, 50, 60 millimeters of mercury range or less. On the return trip, the heart has no influence on the return flow of blood other than pushing more blood down the arteries. The pressure in a vein is somewhere between 0 and 10, which is very, very low and not adequate to push the blood back up into the heart. So the blood has to have its own mechanism to get there, to get back up to the heart. But veins are similar in structure to an artery. It has, the tunica externa, the tunica media, the tunica interna layers. So it's almost the same size. In the models you've seen of the urinary system, you saw that the interior vena cava, the largest vessel in the lower 2/3 of the body, is about the same size of the abdominal aorta, which is the largest vessel, blood vessel, part of the largest blood vessel in the body. So we can calculate how much blood is going through a structure in the body at any given time. So, and we can calculate that in what we call in milliliters per minute. We know how much blood is going through the kidneys. We can calculate the filtration rate in the kidneys. We can calculate the passage of blood through various organs. Now, there's a term here called cardiac output. The cardiac output is how much blood is coming out of the heart in 1 minute. So the cardiac output, a measurement of how much blood the heart is pumping out. So we got about 7 or 8 liters of blood. How much is the heart pumping out every minute with every contraction? So the heart contracts every 7/10 of a second. So every 7/10 of a second, you have a surge of blood leaving the heart. Now the amount of blood coming out in one surge, one contraction, one heartbeat, one pulse, is the amount of blood coming out is called the stroke volume. That's what the SV here on the slide says. The stroke volume, the heart contracts like you're squeezing the water balloon. You squeeze it and a surge of water, you forgot to tie it off, and you squeeze the balloon and the surge of water comes out of the balloon. And that's the stroke volume. And then you do it again, and 7/10 of a second later, you do it again, and you do it again another 7/10 of a second later. Each one of those is the stroke volume. And the stroke volume is a measurable amount of blood. Okay? Typically about 60 or 70 milliliters of blood is coming out of the left and right ventricles. So the stroke volume, if you multiply the stroke volume by the heart rate, so you're measuring the heart rate. So if your stroke volume is 60, so you're sending out 60 milliliters of blood, and your heart rate is 70, then the simple calculation, and I know I'm doing math in public, but 70 times 60 gives you 4,200, which is the cardiac output. The cardiac output is simply the heart rate multiplied by the stroke volume. And so that is the consistent amount of blood going through any organ. Simply by knowing the heart rate and knowing the stroke volume, you can calculate the cardiac output, and that cardiac volume of blood at 4,200. If you calculate 4,200 mils per minute in a healthy individual, that should be the amount of blood that's passing through any organ. So, depending on the, but on the average. So, cardiac output equals heart rate times the stroke volume. The average stroke volume is about 65 to 70 mils per beat. And the average heart rate is somewhere between 60 and 70, depending on how healthy your heart is, or something like that. Yeah. Is it a healthy heart? Is it an old heart? Is it a young heart? Various medications slow down the heart rate into the 50s and 60s. Many people have a resting heart rate that are perfectly healthy in the low 60s or even the high 50s and are perfectly fine with that. Many people have a resting heart rate. The classic is 70 beats a minute, 72 beats a minute. So even if you take 70, as the average heart rate, 70 times a minute, every 7/10 of a second. That's how long the cardiac cycle takes, 7/10 of a second. If you have a stroke volume of 70 and you have a heart rate of 70, then your cardiac output is 4,900, and that's mils per minute. And that's pretty much how you would calculate out our cardiac output. So when we send this blood out through the circulatory system, we are going to be carrying blood that is high in oxygen, rich in nutrients, low in CO2, leaving the left ventricle of the heart going into the aorta and going down to the distributing arteries, down to the arterioles, and down to the capillaries. And at the capillaries, where we are now one cell layer away from a cell, we have a capillary and we have a cell right next to the capillary. Now, every cell in our body, except for our cartilage in our knees, for example, is in contact with at least one capillary. In our lungs, each alveoli has up to 100 capillaries around. But every cell in our body, other than cartilage, will have at least one capillary. Cartilage has to get their oxygen and nutrients through diffusion to the surrounding tissues, which is why cartilage injuries in our bodies take longer to heal. So that's just a little aside there. So we deliver oxygen and nutrients to the cells. The cells are using that oxygen for cellular respiration. There it comes again, that nasty two words. And that's giving off carbon dioxide, and that's but we're using the oxygen, we're generating ATP, we give off CO2. The CO2 is a waste product. As we process nutrients and amino acids, we're going to generate nitrogenous waste. As we process foods in our liver, we're going to release chemicals that we don't want to keep around, that we detoxify. We break down certain chemicals into their harmless state. Those are all collected from the tissues, and then we bring our blood, we send our blood to the kidneys. The kidneys are filtering out everything except the carbon dioxide. The kidneys are going to filter out the nitrogen-bearing waste, the breakdown of proteins. Are going to filter out chemicals that we don't want. All of this is going to be taken out by the kidneys. The liver has detoxified first what we take in. It's the pre-cleaner, as I said. Then we send it through the heart, we pump it to the body. The cells use what's in the blood, the nutrients and the oxygen. They generate their own waste products. Now we have to get rid of those waste products. We send the plasma through the kidneys to get rid of the chemical waste. CO2 is taken to the lungs. Blood comes back to the heart into the right atria, and from there to the right ventricle. Now remember, the heart is a 4-chambered pump. The top 2 chambers are called the atria. The bottom 2 chambers are the ventricles. The atria are fairly passive. They are the receiving chambers. Blood from the body comes in on the right-hand side into the right atria. Blood from the lungs comes in on the left-hand side. They're fairly flaccid, and it passes into the right ventricle and to the left ventricle. When the heart contracts, the right ventricle sends blood to the lungs, where we can get rid of our CO2 and pick up some more oxygen. The blood on the left, which is now enriched with oxygen and fairly clean, is pumped out to the whole body. So the amount of blood pumped from the right side to the lungs is exactly the same as what's pumped to the body. We have to have the same amount of blood going out both chambers. Right side of the lungs, if the right side is pumping 70 mils of blood out, the left side is pumping 70 mils of blood out in a healthy individual. Now, blood comes out of the left ventricle under very high pressure. It's shooting out there. The pressure on the right side is much lower. It's 15 to 20 millimeters of pressure, because we don't want to shoot high pressure blood into the lungs. It'd be like trying to turning on a fire hose on a paper towel. The paper towel would get shredded immediately. Remember, our lungs have the consistency of, just using the analogy of single ply like toilet paper. They're much more fragile than that, because they're a half a micrometer in thickness, but that's the best we can do. So if you were shooting blood from the artery, from the aorta, into the lungs, it would shred the lungs under the high pressure. So we have very low pressure going to the lungs. But to the rest of the body, we're shooting blood under very high pressure, and it's moving pretty fast as it leaves the aorta. I mean, as it goes into the aorta. And it will slow down because we start hitting arteries that we have to send blood into. So this rapid high velocity blood starts slowing down. It goes to the aorta. From the aorta, it immediately branches into three arteries. It has it will go up the left subclavian, the left carotid. It will go into what's known as the brachiocephalic, which has the distinction of the shortest artery in the body. And the brachiocephalic will become the right carotid and the right subclavian. And so we're sending blood out all these arteries, and the pressure is dropping, and the speed, the velocity of the blood is dropping. And as we go further and further away from the heart, we go into more and more arteries and arterioles, and the pressure keeps dropping and the speed of transmission keeps dropping. The capillary beds are the slowest and lowest pressure areas other than the veins. The veins are actually going to be the lowest. But the capillary beds have a low enough pressure and low enough velocity so that the cells can obtain what they want and get rid of what they want to get rid of. So here we see, we see the capillary beds in the middle there. The left is the artery and the right is the venule, and the capillary beds are in the middle. And if we look at the first graph underneath that, we see that peak in the middle, that sort of like a bell curve there. That shows you that's looking at amount of cubic millimeters. To show you the amount of space covered by our blood vessels. So we see at the beginning, on the far left-hand side, we're looking at area of the arteries. It's a very small area that is involved here. But as we get into the capillary beds, it expands drastically. It's like driving on a dirt road and suddenly discovering an 8-lane interstate. Yeah, we have this tremendous surface area. And then once we get through the capillaries, we drop back down to the veins, which has very little surface area. The bottom graph shows how the speed slows way down. We're coming out under high pressure and great velocity. And by the time we get to the arterioles, we drop drastically and we get down to almost no pressure and no velocity. And we start picking up a little bit on the other side. The velocity in the veins is still very slow, and the pressure is less than 10 millimeters of mercury. Now we hear this term blood pressure frequently. Who hasn't had their blood pressure checked? We all have. It's when you go into your healthcare provider, your physician's office, it's the first thing they do is they take your blood pressure and your heart rate and your temperature and your weight. It's just, and your breathing rate. It's all a matter of routine. Usually they put that little pulse oximeter on your finger. They get your saturation level. They get your heart rate at the same time. That makes the vitals, as they say. Now, blood pressure is a very important diagnostic tool. We don't think much of it because it seems like it's part of the routine. But blood pressure is what is very simply the pressure of the blood inside the vessel pushing against the outside wall. That's all it is. And we still use the term from hundreds of years ago when we talk about millimeters of mercury. There's the early blood pressure devices, what we called a sphygmomanometer, it's the old term for it, was based on using a column of mercury in the device. That's back before we knew all the bad things about mercury. So there's actually a column of liquid mercury that would be used to measure the pressure with. So we'd have this little graph, little column, and it looked like a thermometer. And as you go pumping the cuff up on an individual, the pressure would rise in this column of mercury, and you would read it off in the chart. I mean, oh, that's how many millimeters of mercury that we refer to. We still use the same term when we're talking about barometric air pressure. 760 millimeters of mercury air pressure, for example. So, unfortunately, we don't use mercury anymore. We use these little dials and have your blood pressure taken. What it's measuring is the pressure, in those very large arteries. That are, you don't put a blood pressure cuff around someone's neck, but you put it usually around the brachial artery. The brachial artery is the large artery in your it runs along the humerus. So it's in the upper arm. So the blood supply comes up from the aorta, it branches out and gives you typically it's our left arm, and coming off of the aorta is what's known as the left subclavian artery, which runs directly behind your clavicle. That's why they call it subclavian. And this subclavian artery branches into your axillary artery, which is right at your armpit, axillary. And the axillary artery branches into the brachial artery. The brachial artery is in your upper arm, and that's where we measure pressure, right there. And the pressure will always drop as we go further and further away from the heart, because the blood is the volume, the speed of movement is slowing down. We're being distributed into more and more arteries as we go further and further away from the heart. So we try to measure the blood pressure as close to the heart as we can. Okay. So, now this is an extraordinarily busy little slide here. There are a whole variety of mechanisms our body uses or things that will affect our blood pressure. Here's a good one over here. Body size. Individuals with larger body size, larger body mass, for example, has to generate more blood vessels. The process of angiogenesis. As our mass increases, we have to have blood vessels to supply the needs of that mass. And so the more vessels we have, the longer they are. Blood vessels that are more numerous and longer tend to have greater resistance, causing greater pressure. So we see that individuals that have large mass, the larger the body mass, it's almost automatic that the blood pressure will rise with that. There are many things that are going to affect our blood pressure. We see blood pressure can, if blood volume drop, like if we're bleeding, blood volume will drop, blood pressure will drop, the heart rate will go up to compensate for that. Chemicals will cause us to, like norepinephrine. Norepinephrine is a vasoconstrictor. Norepinephrine will cause us to squeeze our blood vessels. It reduces the diameter of the blood vessel. That creates resistance, and our pressure goes up. So, I mean, I could go through all these here. We're going to touch on all of them as we go along. But if you need a quick check on what's happening somewhere, then you can come back and look at this slide. I don't want to go through the whole thing. So what is a good blood pressure? Well, we look at this. For years, we've considered that a systolic pressure, that the systolic pressure gets its term from what we call ventricular systole. Systole is the point of contraction in the heart. So when the ventricles contract, the pressure in the heart will be the greatest. So we look at the systolic pressure. What is the pressure at the point of contraction of the ventricle? Now, then we compare that to the pressure when the ventricle relaxes. We call that the diastolic pressure. So the term systole means contraction, and diastole means relaxation or at rest. So our systolic pressure versus our diastolic pressure. So we measure the pressure with a blood pressure cuff, and we get two numbers. We get a high number and a lower number. The higher number is your systolic pressure. Generally, we like to consider a healthy blood pressure, a systolic value of 120 millimeters of mercury. If you've taken blood pressure, then you know that you release the pressure on the cuff and it drops down slowly, and you will then so the basic principle is you put this cuff around the brachial artery, you pump up the cuff and inflate it, and you block the artery. You have a stethoscope up underneath the edge of the cuff, and you're listening. And you hear nothing other than the noise of the plastic tubing of the stethoscope. And then you start releasing the pressure. When you release the pressure, then you start hearing sounds. And you're hearing the sound of the blood passing against the wall of the artery. It comes out as a thumping sound. And so that first number on your cuff, on your gauge you're looking at, that first number that you see when you first detect that noise, that thumping sound, that's your systolic pressure. If you continue to release the pressure in the cuff, when the sound goes away, that's your diastolic pressure. So diastolic pressure is a very important number because our heart spends most of its time in rest. The contraction portion of the entire cardiac cycle lasts 7/10 of a second. Most of that 7/10 of a second is in diastole. Now, we want the heart to rest. If the pressure is elevated in the diastole stage, it means the heart isn't resting. That's an indicator here of it's probably a greater indicator of high blood pressure than an elevated systolic value. We tend to get more excited if we start seeing our diastolic pressure rising rapidly. So a person that has a pressure of 120 over 80, 120 systolic and 80 diastolic, we consider reasonably healthy. A person that's 120 over 90, we would be very concerned because the diastolic pressure, it's only went up 10 millimeters, but we would be very concerned that pressure has risen too much. Okay. For years, the American Heart Association has tried to push for lowered values as what we consider healthy. So right now, the American Heart Association has tried to say that 120 over 80 is is elevated, where for years we've all been taught that 120 over 80 is a healthy number. So if you look at the chart here, elevated is 120 to 129, and diastolic is less than 80. So they consider that elevated. High blood pressure, hypertension stage 1, they consider that 130 and above over 80 to 89. Now, I will agree with them on the 80 to 89 value as it goes up. I won't agree with them on 80. But generally, if your blood pressure is 120 over 80, it's been considered normal for years. So slightly lower than that is even better. Okay. How do we get how does the blood pressure work? Well, we have to deal with elasticity of the blood vessel because of the smooth muscle lining with the elastic fibers in there, and how much blood is going into the arteries at any given point. The systolic pressure is what happens at contraction of the ventricle. The diastolic pressure is when the ventricles relax after the heartbeat has occurred and the blood has surged out of the ventricles, some going to the lungs, most going to the body. As soon as we do that, we go into diastole. We rest for almost 4/10 of a second, almost 5/10 of a second. And the actual contraction phase is very brief. So we're spending a great deal of time in diastole. And the reason we do that is this is when the heart's reloading. When we go into diastole, the heart contracts, it fires, blood surges out, that was the systolic phase. Now we go into a rest phase for 4/10 of a second. When we go into the rest phase, that's when more blood is coming into the heart. That is when the ventricles are reloading. The ventricles are filling back up again to contract, at the beginning of the next cardiac cycle. If the pressure is high in the ventricles and here during the resting phase, it's more difficult to get blood in. There is resistance. So we don't want to have this high pressure, but blood flow into the ventricles is mostly dependent on a passive flow. 80% of the blood flow into the ventricles during the rest stage is passive. So but only the last 20% where the atria contract is forceful. If we have to work harder to get the blood into the ventricles, then we're going to have a higher heart rate. If we work harder to put blood into the ventricles, we're going to pump less blood during a contraction. If we pump less blood, then we're going to have to increase the heart rate to compensate. If we increase the heart rate, we're going to raise our blood pressure. So if we're not resting properly during diastole, we're not getting an adequate amount of blood coming. So the compensation is be faster, be more frequently. So new term here, what we call the pulse pressure. So we know what the systolic pressure is. That's the pressure at the point of contraction. We know what diastolic is. That's the pressure in the blood at the point of relaxation of the heart. The pulse pressure is simply the difference, the mathematical difference, there I use that math word again, between systolic and diastolic. And so we can determine the pulse pressure by simply subtracting the diastolic from the systolic. If our systolic is 120 and our diastolic is 80, our pulse pressure is the difference, which is 40. 120 minus 80 equals 40. Even I can do that. So we can use that value then to calculate what we term the mean arterial pressure. Another term, mean arterial pressure. This is the pressure that's going to drive the blood through our tissues. This is the number we're looking for. We've got diastolic, we got systolic pressure, we got diastolic pressure. We've taken our blood pressure with a sphygmomanometer, a blood pressure cuff. We have a value. And we subtract the systolic, we subtract the diastolic from the systolic. If our blood pressure is 110 over 80, then our pulse pressure is 30. If our blood pressure is 120 over 80, our pulse pressure is 40. If it is 130 over 80, then our pulse pressure is 50. So now the mean arterial pressure is easily calculated. You take the diastolic value, let's say your diastolic pressure was 80, plus 1/3 of the pulse pressure. Now your pulse pressure, in this example here, the diastolic value was 80, the systolic was 110, the pulse pressure was 30. So we take to get our mean arterial pressure, there's a reason for all this, just bear with me. The mean arterial pressure is the diastolic value, in this case was 80, plus 1/3 of the pulse pressure, which was 30. So that gives us a mean arterial pressure of 90 millimeters of mercury. So what's that mean? Well, we know that as long as our mean arterial pressure is above 60, then we have enough pressure to adequately perfuse the tissues. Now, what have we done that was so difficult? that were invasive, nothing. We took the blood pressure. We took the blood pressure and we determined the pulse pressure. We took the diastolic value from the blood pressure and added 1/3 of the pulse pressure to it. That gives you the average, the mean arterial pressure. And so using that, will that tell us that we have adequate perfusion in the tissues? If it's above 60 millimeters of mercury, it is working. If it's less than 60, it means that our pressure is not sufficient to supply the needs of the tissues. Yeah. And all we've done to determine that is take the blood pressure. And that gives us these numbers. We haven't had to do any kind of invasive testing. We just take the blood pressure, take the diastolic minus the pulse pressure, not diastolic plus 1/3 of the pulse pressure, gives us your mean arterial pressure. And now you have another tool to determine if your individual is adequately perfusing their tissues. And why is that important? Why is the mean arterial pressure and the pulse pressure important? Well, of course, we know what the pulse is. The pulse is the representation of the heart rate. The pulse is not the heartbeat. The heartbeat is the sound of the valves closing. The valves between the atria and the ventricles, and the valves at the pulmonary artery and the aorta. So heartbeat and pulse are two different things. Pulse is the snapping back of the arterial wall, but that is equivalent to the heart rate. So if we detect a pulse of 70, then that means that the heart has been contracted 70 times in a minute. Now the pulse pressure is an indicator, a change in pulse pressure over time. If you're taking the pulse pressure, if you're watching it gradually change over time, and increase over time, this is a red flag for atherosclerosis, what we call the hardening of the arteries disease, or just plain old heart disease. Atherosclerosis, generic term, hardening of the arteries, sort of like, it's like people say sugar diabetes. Well, they say hardening of the arteries. What's happening here is cholesterol is accumulating in the coronary arteries. Cholesterol starts accumulating in the coronary arteries and in the arteries in the brain, and they're narrowing the arteries. What happens is that we have excessive levels of fat in our diet. We tend to have, and fat is important, and cholesterol is important because we need both in our diet. Excessive levels of cholesterol and fat, we tend to deposit excess cholesterol, or that triggers these fatty deposits on the inside of the arteries, and they start narrowing the arteries. They start building up and accumulating to where someone can be functioning with 95% blockage of one of the major coronary arteries, and they're just prone. They're just a myocardial infarction waiting to happen, what we call a heart attack. So, but this is another way. The pulse pressure, in addition to using it to calculate mean arterial pressure and look at perfusion, the pulse pressure can also be your first flag on, well, your pulse pressure has been rising steadily. We might want to consider, X, Y, and Z, because, this is one of the red flags for hardening of the arteries. Non-invasive, no CT scan, no treadmill, no ultrasound. Just this is the first flag. Saying, hey, this might be of concern because we're seeing a gradual rise in the pulse pressure over time. So this is what the arteries look like with this hardening of the arteries. It's generally thought to be triggered by cholesterol Cholesterol accumulates in these vessels. You can see in the left, the deposit is referred to as plaque. Plaque continues to grow as more and more fatty deposits are left there, brought in by the cholesterol. Uh, and on the right is what, if you were to open up the artery, that's what it looks like. Here, these are the fatty deposits on the artery. Uh, you know, I always think it looks like cheese Danish myself, or maybe one of those little tiny little pizza things, you know. Uh, anyway, I don't want to ruin too many food groups today, but this is what happens. Now, we talked in AP1 about the role of the low density lipoproteins and the high density lipoproteins. I'll just touch on that briefly here. The LDLs are what we call the good cholesterol. The low density lipoproteins are responsible for removing cholesterol from our blood. See, the HDLs, the high density lipoproteins, take cholesterol out to the tissues because our cells need that. They come, we're releasing the HDLs to carry cholesterol out there. The cells need cholesterol to make steroids, for one thing. They use it for structural support inside the cell membranes. But the HDLs don't bring them back. So we have excessive cholesterol. The HDLs leave them in the tissue areas. The LDLs, the low density lipoproteins, essentially bring the excess cholesterol back to the liver for destruction. So we'd like to see our LDL numbers good and our HDL numbers low, because that means that we have maintaining a healthy diet and a healthy heart. The greater the HDL numbers in our blood, the more likelihood that we're going to end up in a situation like we see in the pictures here, with fatty deposits accumulating inside the coronary arteries and the cerebral arteries. So it runs the risk of a heart attack or a stroke in an individual as these arteries become narrowed. And typically, it'll occur during high stress. The individual is walking around with 95% blockage, and what would usually happen is that there will be a stressful incident which will cause a demand of blood through the heart, and the artery is narrowed and the heart can't keep up with the demand. Or a platelet will bounce against this rough surface and trigger the formation of a clot and complete the blockage of the vessel. And we see here, there's a partially occluded artery on the left. It's probably 60% occluded. On the right is one that looks like it's about 90% blocked. You have very little blood flow getting in there. Now, the heart will develop workarounds. It will generate through angiogenesis, since the tissue downstream needs oxygen and needs nutrients. And the heart doesn't get it from what's going through the ventricles. It has its own blood supply. And that's what's getting blocked here. The heart will develop through angiogenesis little workaround vessels around the blockage, but they can't meet the demand of the stress. So if your patient decides to run up a flight of stairs and suddenly has a massive blockage in one of these coronary arteries, they're in a world of hurt. So because the workaround can't help, it's too tiny, it's insufficient to meet the demand. See, what they run into is what we call resistance. Resistance, these little tiny vessels don't allow the flow through here, and so there's you can't force, you can't take a large diameter pipe where something's, water's running through an 8-inch pipe at high pressure. You can't just stick it immediately, connect that to a garden hose and expect the garden hose to function. The garden hose will explode because of the high pressure. So this is what happens here if we go from a large artery in the heart that suddenly it's hitting this blockage, and we go from the large bore artery, these little tiny arterioles trying to work around the blockage. resistance is critical in our circulatory system and in the heart itself. Um, resistance is the peripheral resistance that we encounter in a blood vessel. Now, we have resistance can be caused by any number of things. This is in the circulation throughout our bodies. It is friction. It is the opposition of the flow. It's like when you're in Walmart and you've got your buggy, you turn a corner into an aisle and you discover that everybody's coming towards you and you're going want to go the other way, and you've got 30 people coming towards you and you're trying to push your way through there and you can't get over into the other side of the aisle because there are people in there too. So you know what resistance is. You're trying to, people don't like to get knocked down with the buggy. You know? Just saying. Okay. Resistance. What causes resistance? Well, the first thing, three things that can affect us. The viscosity of the blood. We know that blood is somewhat sticky. It's as they say, it's thicker than water. That's one of those old wives sayings that is actually true. Blood is thicker than water. Viscosity of blood is greater than water. The average viscosity of blood is sort of like chocolate syrup. I've said that before, but it's a good analogy. So viscosity, we can't do anything about blood viscosity. Blood viscosity is going to be a constant, so we can't change that at all. But it's, the thickness of the blood does create friction. The thickness of the blood, the viscosity of the blood, it does create friction, and friction creates resistance. So it makes it, there is a constant friction, resistance of blood flows through a vessel. The vessel length. Longer vessels have greater resistance than shorter vessels. But we're sort of stuck with the length of the vessel. The abdominal aorta goes through the diaphragm and goes all the way down to the inguinal region before it branches off. That's a very large and long vessel. The femoral artery comes off and goes down your leg on each side, and those are long vessels. We can't do anything about that. The longer the vessel, the greater the resistance is going to be. We're sort of stuck with the length of the vessel. The only thing that we can change, which alters resistance, is the size, the diameter of the vessel. The diameter of the vessel can be changed by our sympathetic nervous system. Or we can change the diameter by packing the vessel full of plaque and narrowing the vessel. Our peripheral resistance is based on diameter of the arterioles in our body. We can control the arterial size. It's the autonomic nervous system, so we have no direct control over it. It's done automatically by the sympathetic nervous system, releasing the neurotransmitter norepinephrine that causes the smooth muscles around the arterial. If we release norepinephrine, the smooth muscle constricts and narrows the opening of the vessel. If we don't release norepinephrine, the vessel relaxes, the smooth muscle relaxes, and the diameter enlarges. We say we either vasoconstrict or vasodilate. So it is all under the control of the sympathetic nervous system. It's either release norepinephrine for vasoconstriction or don't release norepinephrine for vasodilation. Now, that is a perfectly normal response to changes in what's going on around us. Plaque accumulation interferes with this process. If we start narrowing the interior of the arteries with fatty deposits called plaque, then we reduce the diameter, and we can't change that. We can't get that plaque to come out unless we change our lifestyle, or maybe we have to have some sort of intervention, with catheterization, perhaps with angioplasty, the mechanism where you go in and put a stent in and open up the blocked artery. That's not as drastic as bypass surgery, but it's still an intervention here. The normal changes in the diameter of our vessels is done under the control of the sympathetic nervous system. Plaque in an artery is not going to change. It's going to get bigger. It's going to increase the friction, increase the resistance, and increase the likelihood of a clot forming based on a random platelet bouncing against this rough surface of the plaque and attracting all of its friends and neighbors. So if you look at the illustration here of the vessels, which one has the greatest resistance? Well, the longer the vessel is, the more resistance you have. The smaller the diameter, the more resistance you have. So while number 2 is a long vessel, it also has a very large diameter. If you look at number 3, it's a short vessel with a large diameter, so it's got the least resistance. Number 4, long vessel, narrow diameter. It will have the greatest resistance. Even number 1, which has a narrow diameter, is only short. It's very short. So it's not going to have a lot of resistance. The bottom one, the longer the vessel it is, the smaller the diameter, the greater resistance you're going to have for blood flow going through here. The pressure will always be higher in a vessel like number 4. So the process of vasoconstriction and vasodilation, this is what we can use to open or close blood vessels. Vasoconstriction. When we stimulate the smooth muscle lining of the vessel, the smooth muscle will constrict, dump norepinephrine into the vessel. The smooth muscle will contract, and the vessel will constrict. And you look at the blood vessel on the left, and you see that the diameter has decreased. We have a much the smooth muscle has constricted. You can see the smooth muscle layer right underneath the surface coating here, and it's much thicker. If we stop releasing, and it's caused by norepinephrine from the sympathetic nervous system, if we stop releasing norepinephrine, then the smooth muscle relaxes. And this is the same vessel over here on the right that has now vasodilated. The smooth muscles surrounding the artery have relaxed. The diameter enlarges. We are vasodilated, and we have a greater blood flow on here. And the blood pressure in that artery has dropped. When we constrict a vessel, the pressure will go up. When we dilate a vessel, the pressure will go down. And this is primarily taking place in the arterioles in our blood supply. Here we see, look at a vessel at the top there. There is the release of norepinephrine here on a constant basis. The vessel is maintaining what we call sympathetic tone. It is slightly constricted, slightly vasoconstricted, but it is mostly open. Just like muscle tone, we have sympathetic tone here to have the vessel just a little constricted, ready to vasoconstrict or to relax completely. And so we have we're releasing our signals from the sympathetic neuron here are releasing norepinephrine onto that vessel at a constant rate. But here at the bottom left, we release a much larger dose of norepinephrine at a much faster, well, actually it's not a larger dose, it's just at a faster rate. So it is the effect of a larger dose, but really it's just like action potentials. There's no such thing as a large action potential or a small one. They're all the same. You just increase the frequency. The same thing here. We're just increasing the frequency of release, and we have greater constriction of the smooth muscle, and we narrow the diameter, and we have a fully constricted vessel. And on the right, we have reduced the frequency significantly of the release of norepinephrine, and the vessel dilates, the diameter gets larger, and more blood's going through here, and the pressure is lower. So it is all under the control of the neurotransmitter norepinephrine. Here we see the same vessel. The one on the left is vasodilated. The one on the right is vasoconstricted. The one on the left was receiving very little stimulus from norepinephrine. The frequency of release was very slow. The one on the right, the frequency of release increased rapidly, and so we get this very quick constriction of the arteriole. Okay, a couple terms here that you probably will need to remember. Yeah. Blood pressure is equal to the cardiac output times the peripheral resistance. Well, you're not going to be able to measure peripheral resistance directly, so you can take blood pressure, and that will give you your, that will be your indicator for you of, is there resistance or not. Cardiac output is heart rate times the stroke volume. Again, it will be difficult to determine actual stroke volumes, but you'll know the heart rate. So now if you want to calculate the stroke volume, the term here is the end diastolic volume, that's EDV. We're going to talk a lot about that when we get into the heart. But the end diastolic volume, that is when the heart is in its rest phase, the diastole phase, that's where diastolic volume comes from. So the heart's at rest. Blood is flowing in passively to the ventricles. The ventricles are filling up and filling up and filling up. The ventricles get to about 80% full, passive influx. All the valves between the atria and the ventricles are wide open. Blood's flowing in here, just trickling in, and the ventricles are filling up. They get to about 80% full. The atria then contract and squeeze about another 20% of blood, topping off the ventricles. When the atria contract and dump that extra 20% of blood into the ventricles, that volume, whatever that is the end diastolic volume, because of the atrial contraction signifies the end of the rest phase. That's the end of the diastolic phase, or the end of diastole. So typically the end diastolic volume is somewhere around 120 to 130 milliliters of blood on each side. Now, the end systolic volume is what is left in the ventricles after contraction. So the ventricles contract and they eject about half of what's inside. So if your end diastolic volume is 130, you might eject out 60 mils of blood and leave about 70 mils behind. That's our reserve, because we don't want to discharge all the blood at one time. We want to have a reserve because, maybe we're only walking down the street and pumping blood and pumping 60 mils out, but maybe we have to suddenly run across the street to avoid being hit by a vehicle. Now our heart rate is way up. Our end systolic volume is lower because we're sending more blood out. But a person at rest, the end diastolic volume is going to be about 130, 110, 120, 130, somewhere in there. The end systolic volume is going to be what's left over, about 60 or 70 mils. So our stroke volume is the end diastolic volume minus the end systolic volume. Stroke volumes are going to run between 60 and 70 mils on average. So so your stroke volume then is simply subtracting the end systolic volume from the end diastolic volume. And then your cardiac output is your heart rate times your systolic volume. So if what's left over, I'm sorry, a stroke volume, your stroke volume is what's left. They're calculating what went out. If your total amount of blood in your heart at rest was 130, and you have 70 mils left, that means that the amount you pumped out was 60 mils. That's your stroke volume. Your cardiac output is your heart rate times the stroke volume. So if your stroke volume was 60 and your heart rate is 70, your cardiac output is 4,200 mils per minute. So you can calculate a lot of this just with just a few of these numbers. So things to remember: anything that's going to affect your cardiac output or your peripheral resistance is going to affect blood pressure. A person who has gained weight and has increased their blood flow because they've increased blood vessels, they're going to be increasing their peripheral resistance. Their cardiac output will go up to meet the demand of the extra cells that they've laid on. That will raise their blood pressure. So cardiac output increases, blood pressure goes up. Peripheral resistance increases, blood pressure goes up. A person goes in on a much narrower scale, forget the weight loss, just a person goes into a crisis event. The cardiac output goes way up. They're responding to some sort of some sort of fight or flight response. But they are experiencing a fight or flight response. The cardiac output will go way up. Their blood pressure will go up correspondingly as the output goes up. But that's a short-term event. Long-term changes in blood pressure occur through weight gain, weight loss, exercise, things like that. If the cardiac output or the peripheral resistance goes up, blood pressure goes up. If the cardiac output drops or the peripheral resistance drops, blood pressure drops. A person who has experienced a significant weight reduction to get to what we consider a healthier rate, a healthier weight, will have less blood vessels because they'll have less tissue to meet the feed, and basically, and then that will, with less blood vessels, you'll have less blood. So your peripheral resistance will drop, and the cardiac output will drop, and blood pressure will go down. So, a person who loses weight has a healthier blood pressure than they had before, simply because there's less blood vessels, less blood volume. The heart has to work less. Okay. So to maintain our blood pressure, we like to be, we don't like to be fluctuating all over the place. Our heart and our blood vessels and our kidneys, how the kidneys communicate. There's those kidneys. What other organ in our body monitors our blood constantly, monitoring pressure and monitoring oxygen levels and monitoring sodium levels and monitoring water levels, and monitoring red cell levels. What other organ does all that for us? It's the kidneys. Now, we maintain blood pressure through our medulla oblongata. We have medulla oblongata in the brainstem. It's going to monitor heart rate. It's going to monitor blood pH. It's going to be getting information on sodium levels, and the medulla will determine our blood pressure. What our blood pressure is going to be to determine how we're going to respond. It detects pressure changes in our bodies. We have what are called baroreceptors embedded in the aortic arch coming up out of the heart that monitors the pressure there. They're simple mechanical receptors that deal with pressure. And we have pressure receptors in our carotid sinus. The carotid sinus is that spot about an inch or so below the bottom of our earlobes, just underneath the mandible, where we can detect the carotid pulse. So the carotid pulse there to carotid sinus, we have baroreceptors there monitoring our blood pressure, and that's feeding the medulla. So the medulla knows if our pressure's up, if our pressure's down, it knows our heart rate, it knows our carbon dioxide levels in our blood by detecting pH. Unfortunately, the medulla already, can't distinguish why we're having a pH change. So they can't distinguish between ketoacidosis and accumulation of CO2. But other than that, it does a pretty good job of monitoring pH for us. So all of these are going to work together. The brain, the medulla oblongata and the brainstem is going to stimulate the heart rate or slow it down. It's going to trigger the autonomic system to dilate vessels or constrict vessels with norepinephrine. The kidneys will determine blood pressure also by the sodium concentration in the filtrate coming through the distal tubule, because in the kidneys, if the
My
sodium,
doctor prescribed me Vyvanse yesterday,
if the
so I'm ready for the come in.
Yeah.
if the kidneys detect, if the kidneys detect
I think I know what that is.
low sodium,
Oh, really?
hey, I need someone to mute
Process is different or something like that.
this. Okay, right here. If the kidneys detect low sodium in their filtrate, and we'll talk about this in the kidney lecture, it means that the blood pressure may be very low, because if sodium levels in the filtrate are low, it means that the movement of the filtrate is slow, meaning that we have more time to suck out sodium. I probably got you all confused in that. So, but the kidneys are doing their job. They're monitoring everything. So what affects blood pressure? Well, cardiac output. The more blood we pump, the higher the greater the stroke volume, more blood coming out, or the increase in the heart rate. If the heart rate increases or the stroke volume increases or they both increase, our cardiac output's going to go up, and that's going to cause a rise in blood pressure. If resistance increases, if we have blockages in our coronary arteries, we have blockages in our cerebral arteries, we're going to, if we have narrowing of arteries in the heart, we're going to have an increase in blood pressure. If our blood volume goes up, we will see an increase in blood pressure. If our blood volume will go up if we increase in body mass. So all of these will affect our blood pressure. Can't emphasize this enough. Cardiac output. A couple things are at play here. Cardiac output is determined by how much blood's coming back to the heart. How much blood is returning? If we have a great deal of blood returning to the heart, if we have, lots, we have many vessels, a larger body mass, and we have more blood coming back to the heart, that's going to affect the cardiac output. It's going to increase the amount of blood that's in the ventricles. If there are greater demands, we're going to have to pump more blood. That raises blood pressure. Now, the heart rate can be controlled. Cardiac output is driven by the amount of blood coming back in. The heart rate can be controlled by the medulla, or is controlled by the medulla. The heart rate is dependent on two nerves. We have the vagus nerve coming out of the cardiac inhibitory center of the medulla. And the vagus nerve will dump acetylcholine into the heart, and that will slow down the heart. So it can slow it down. And if we stimulate the vagus nerve too much, we can slow down the heart to where it stops. I think we mentioned that the other day about increasing the abdominal pressure, stimulating the vagus nerve, and a person, bagels out while they're on the toilet if they have heart issues. The cardiac nerve, on the other hand, coming from the cardiac acceleratory center in the medulla, releases epinephrine into the heart, which will increase the heart rate. So we can either speed the heart rate up or slow it down. Now, the cardiac inhibitory center is under the control of the parasympathetic system. So that's the dominant system. We use acetylcholine all the time. So remember, the sympathetic side is going to release epinephrine and norepinephrine. Epinephrine that raises the heart rate. That's a sympathetic response. But remember, that's not the dominant side of the autonomic system. We primarily run parasympathetic, rest, digest, defecate side. So we're pretty much using the acetylcholine through the vagus nerve to control our heart rate. We can accelerate our heart rate, or we can slow it down depending on are we releasing acetylcholine or not. So if our stroke volume, so we got cardiac output controlled by the amount of blood coming. The heart rate is controlled by the medulla, either through the cardiac nerve or the vagus nerve. Stroke volume is controlled by how much blood we have in the ventricles. So cardiac output is determined by blood coming in. How much do we actually have in the ventricles will determine the stroke volume. We may be only strong enough to pump a small fraction of that blood that's returning. Stroke volume is typically about 60 or 70 mils of blood per contraction. Well, if the heart is weak, we may be only getting 40 mils. We may not be getting enough blood out to the body. So that leads to all sorts of other complications. Typically, an individual, a healthy individual, has a cardiac output of about 4,800 mils per minute. The stroke volume is around 60 or 70 mils, with an average heart rate of around 70 beats a minute. We can increase the heart rate and increase the stroke volume when we get stressed. When we go into a fight or flight, or we just walk up a flight of stairs. Or you run to the car on a rainy day. You come out of the building and it's raining, and you run out to your car so you can get into the car quicker. So, some simple exercise. You get up out of your chair and you walk. Take a 3-mile walk around your neighborhood, or whatever. You're increasing your activity level. Maybe you're under stress. Maybe you're running away from a dog that's trying to bite you. Your stress level goes up. Any number of things can trigger an increase in the heart rate. Heart rate goes up, stroke volume goes up under any kind of exercise or physical stress. Well, exercise is considered physical stress because you're changing what you're doing. So the cardiac output is going to change. You're going to be sending more blood back to the heart. You're going to be pumping more blood out of the heart. Your heart rate's up. Your cardiac output is up, and your stroke volume's up. But then it's going to come back to normal. So, bottom line, more blood coming in is going to affect the cardiac output. Increase the heart rate by releasing epinephrine into the heart. You're going to change your cardiac output. Release acetylcholine into the heart, you're going to drop your cardiac output. All these things can affect, it is a minute by minute change. Because if you're sitting right now, and then when we're done in class this morning, you get up and go walk around, your heart rate's going to go up, your cardiac output's going to go up, because your stroke volume is going to go up. Your heart's going to be becoming a little more efficient there while you're walking around and go to work, whatever you do. Now, cardiac output. These are all the things that can affect cardiac output. It's a dance between the sympathetic and parasympathetic sides. The parasympathetic sides, the parasympathetic side is dominant, which usually is. It's going to keep our heart rate and our cardiac output at a constant, resting level. If we become more active, we're going to be releasing epinephrine, causing our heart rate to go up, our cardiac output, and our stroke volume going up. Just, it's a constant dance back and forth. There we go. The important point here. The stroke volumes have to be equal. The stroke volume from the right ventricle has to match the stroke volume on the left ventricle. If the stroke volume on the right side is pumping out 70 mils of blood, the right ventricle is sending 70 mils of blood to the lungs. That's where it's going to go and become, it's going to become enriched with oxygen. Because that's what blood does. It leaves the right ventricle, goes to the lungs, it picks up more oxygen, and then it comes back to the left atria and goes into the left ventricle. And that 70 mils of blood is going to get pumped out to the systemic circulation. So 70 mils goes to the lungs, it gets oxygenated, it comes back to the left atria, goes into the left ventricle, and it's pumped to the body. But what if the left ventricle isn't strong enough to pump 70 mils? What if the left ventricle can only pump 50 mils of blood? And you're sending 70 mils to the lungs, and 70 mils is coming back from the lungs, going to the left ventricle, but the left ventricle only pumps 50. What happens to the other 20 mils of blood? Well, it backs up in the lungs. You get swelling, you get a fluid accumulation in here, simply because the left side of the heart couldn't keep up with the right side. So the stroke volume has to be the same. If 70 mils of blood goes out of the right ventricle and it comes back to the left ventricle, then the left ventricle has to pump 70 mils out to the body. There's no accumulating of fluid in the lungs. Now, what happens if the right ventricle can't do the job? What if the left ventricle is sending 70 mils of blood out to the body, and 70 mils of blood comes back to the right side of the heart and goes into the right ventricle, but the right ventricle is weak and only pumps 50 mils of blood to the lungs. So instead of 70 mils going to the lungs, we only have 50 mils going to the lungs, which means only 50 mils comes back to the is coming to the right, to the left ventricle. What's happening? What happened to the other 20 mils again? If the right ventricle can't keep up with the left side, then we're going to see fluid accumulation in the body. That plasma and blood volume has to go somewhere. And so we'll see swelling and edema taking place in the body. So the stroke volumes from both sides in a healthy heart have to be exactly the same. Otherwise, we're going to see accumulation somewhere of fluid where we don't want to see it. We're going to see the heart unable to complete it, to do its job. It won't be pumping an adequate amount of blood somewhere, either to the lungs or to the body. Now, I probably already touched on this earlier, but I can't resist the urge to talk about it again. Blood pressure in the capillaries is usually pretty low. 15 to 35 millimeters of mercury. That's about the same pressure of the blood that's leaving the right ventricle, going into the pulmonary trunk, going to the lungs. The lungs are squishy tissue, and they can be torn apart. If you keep the pressure very low going into the lungs. The pressure going into the capillaries throughout the body is very low. High pressure blood would destroy the capillaries. So we keep the pressure 15 millimeters, nice low pressure. We don't need high pressure blood because oxygen will diffuse automatically from the blood to the cells. Carbon dioxide will diffuse automatically from the blood to the cells. Glucose will easily transfer from the blood into the tissues. If our blood pressure is too high, then we don't have time to dump off the oxygen. We don't have adequate time to dump the glucose. We don't have enough time to pick up the waste products. So a higher blood pressure makes it more difficult for the cells to be adequately as they say, perfused to get their nutrients, to get their oxygen, to get rid of their waste products, or release of hormones. Hormones are circulating in the plasma. You know, hormones are looking for their target cells. If we are not giving the hormones enough adequate time to perfuse, to diffuse across membranes or to get to the tissues, you know, regardless of whether they are requiring a second messenger or they have direct gene activation, like steroid hormone, they're not going to be able to function. You know, the higher the pressure, the less opportunity we are for to recover waste products and to drop off nutrients and oxygen. You know, higher pressure in the kidneys forces the kidneys to filtrate, to filter at a higher rate. And so what will happen is it won't get rid of all the waste products. The higher the filtration rate, the faster the filtration rate in the kidneys means that blood's going through the kidneys so fast that we're not getting rid of the waste. The waste will accumulate, and eventually the kidneys will fail. And I think we saw this earlier, but we'll look at it again here. Here we see our systolic pressure and our mean arterial pressure and our diastolic pressure. We see the greatest drop occurs here in the arterioles. The drop is the most dramatic from arteries here to the capillaries. This area where the arterioles are, we take a significant drop in pressure right there, which is to be expected because the arterioles are where, you know, those are the connectors to the capillaries. We have to have that drop so the capillaries aren't blown apart by the high pressure. So how does our body control blood pressure? Well, we touched on that a little bit with the role of renin, angiotensin, and aldosterone. And that's one way to control blood pressure. But we have a variety of mechanisms we can employ. We have the nervous system at work here. We have certain hormones and chemicals in the blood. We can alter the second by second changes in our bodies that takes place. Because we can alter blood pressure primarily through controlling peripheral resistance. There are lots of short-term changes. You know, every time we get up or sit down, we're going to see a change in our blood pressure. We adapt. We can adapt to those changes. Every time we have a change, we're going to respond to it. We're going to respond to getting up and walking around. We're going to respond to sitting down, with less demand. These are all short-term controls. Long-term controls require changes in blood volume, either raising blood volume or lowering blood volume. So from our nervous system, if we want to regulate blood pressure, we control peripheral resistance. We alter the diameter of the vessels. The arterioles are the ones that have the most impact on blood pressure. So we may have a specific demand. An organ may have a greater demand at one time or another. We meet these demands. Maybe we're working out. Maybe we're lifting weights. We're sending more blood to our skeletal muscles. Maybe we are running. Maybe we are playing a sport of some sort. And depending on the demands on our body, we have to change the peripheral resistance. We have to increase blood flow, for example, to our lungs. We have to increase blood flow to our skeletal muscles. Maybe we have to increase blood flow to our smooth muscle. Whatever the demand is, a large meal. You know, we are processing food through our digestive system, and we need to be absorbing those nutrients in the small intestine, probably starting about an hour after we process. So we're increasing the blood flow to pick up those nutrients. So we have demands. We have to increase the flow in some areas and perhaps decrease the flow in other areas. So we do this by changing the diameter of the vessel. alter the size of the arteriole, increase the flow, or decrease the flow. We monitor the pressure. We monitor pressure changes all the time. Pressure changes, the baroreceptors are going to tell us, if our pressure is too high or too low. And so, it's depending on the demands, depending on what our pressure is. If our blood pressure has gotten too high because of exercise, we are going to vasodilate to increase blood flow. But that will help lower our increase the diameter, blood going through there, less resistance means less blood pressure. So we monitor our pressure in the baroreceptors, in the carotid sinuses and the aortic arch. That tells the medulla, do we pick up the heart rate? Do we slow down the heart rate? Do we dilate the arterioles, or do we constrict the arterioles? So our smooth muscle around the vessels, is sort of the ultimate determiner here of what's going to happen pressure-wise and flow-wise. Dilate or constrict. Increase the heart rate, lower the heart rate. And we're detecting that on the pressure or the various demands. So these are all short-term fixes. Your pressure goes up for whatever reason. You walk up a flight of stairs, your pressure goes up. Your pressure's not going to stay up. That's a short-term response. You are sending more blood to your muscles, so your heart's beating faster. You'll have a brief rise in blood pressure as you walk up a flight of stairs, and then it will come back down. The demand is no longer there to have more blood flow to the muscles. You don't walk up a flight of stairs and have your blood pressure shoot up to 140/90, and it stays there. It meets the temporary response. It meets the temporary need, and then it comes back down to your normal level. And it does that, by dilating vessels or constricting vessels or telling the heart to beat faster, whatever we need to do, detecting changes in pressure, whatever we need to do to make it work. But then as soon as the demand is gone, we go back down to our normal level. What we call the vasomotor center is located in the medulla. And this will be the trigger for releasing the norepinephrine. We have muscle tone, we have blood vessel tone, we have muscle tone in blood vessel muscles, smooth muscles surrounding the blood vessels. They have that muscle tone just like we have in skeletal muscle. I showed you that diagram earlier where you had the individual spikes for each release of norepinephrine, and they were at a very sort of what looked like a slower pace. But we maintain muscle tone by releasing norepinephrine on a very slow pace, not where we vasodilate drastically, but where we just sort of maintain a very slight contraction so that we can contract quicker if we need to. It keeps the muscle warm, keeps the muscle ready. So we're slightly innervating the smooth muscle and the arterioles. And so we're always ready to vasoconstrict when we need to. Now, the cardiovascular center is this vasomotor center and the cardiac center. It's all in the medulla oblongata. So the cardiac center tells us to raise or lower our heart rate. The cardiac center uses the vagus nerve to dump norepinephrine, to dump acetylcholine into the heart to slow us down, or it uses the cardiac nerve to dump epinephrine into the heart to speed up the rate. So again, this is a short term. Your heart rate, we tell our heart to speed up, and it doesn't stay sped up, it slows back down. We vasoconstrict the arterioles and they don't stay constricted, they relax and our pressure drops. So we bring our heart rate and our blood pressure back down to normal when we stop the stimulus. That's why it's all short term. It's all part of the sympathetic nervous system here. We can detect just about anything with the medulla. Because the sympathetic side is going to be the active side, causing vasoconstriction and a rise in blood pressure. Remember, when we constrict the vessels, we reduce the diameter, we increase the resistance, pressure goes up. And if we dilate the vessels by reducing the release of norepinephrine, our blood pressure drops. So we monitor all sorts of things. We monitor our blood pressure all the time at the baroreceptors. We monitor our oxygen levels. We monitor our CO2 levels. We monitor CO2 levels indirectly by pH. We monitor hydrogen ion levels indirectly by pH. We monitor the presence of chemicals in our blood. We detect hormones. The hypothalamus is very active in here. And so we're aware, chemically aware, and we are chemically and mechanically aware of what's going on all the time. So we respond. You get up out of a chair, you sit back down. You ever get up out of a recliner too fast, or jump up out of a chair too fast, and you get a little dizzy? It's because your short-term controls didn't quite catch up fast enough because you've elevated yourself from a reclining position to a standing position, and you haven't quite had a chance to vasoconstrict certain vessels to increase the blood flow to the brain and to your heart and your muscles. And so just for a second, you might be dizzy. And then the baroreceptors kick in. There's been a change in blood pressure because the blood volume has dropped because we stood up and blood responds to gravity. So we stood up. Now the pressure changes. We say we beat faster, vasoconstrict, and our blood comes up. We're no longer dizzy. It happens. The baroreceptors on their own play a very important role too. Baroreceptors can respond to a rise in blood pressure. They're not just there to tell us what to do, we've detected a change in blood pressure. Blood pressure has dropped. We need to increase the activity. The baroreceptors will detect a rise in blood pressure. Yeah. You're running up a flight of stairs. You're late for class. I don't know why you're class, but I don't know why you're running up a flight of stairs, but you're running up a flight of stairs and your heart's beating faster and your muscles are active because you're stressed, maybe you're at the beginning of a fight or flight response. I don't know. The baroreceptors will detect this change in blood pressure. Oh, our blood pressure is going up. Well, let's counteract that. And it will trigger the vasodilation of our vessels. It will increase the blood flow. Blood pressure goes up because the heart's beating faster to meet a demand. That's the primary cause of an increase in blood pressure. You have a new demand. You're running up a flight of stairs. The heart has the demand to supply more blood to your muscles and your lungs. You're running up a flight of stairs, and your pressure goes up because the heart's beating faster to meet that demand. That increase in heart rate causes the increase in pressure. The baroreceptors detect that and say, "Hey, we can help this by dilating more vessels, increasing more blood." Because the only reason the heart's beating faster is to send more blood. It's the only reason it's beating faster. It's trying to send as much blood as it can to the muscles, skeletal muscles, and to the lungs. That's the only reason it's beating faster. And the baroreceptors can help alleviate that problem by increasing the diameter of the vessels, relaxing the more arterioles, and allowing more blood flow so the heart doesn't have to beat as fast. That's basically what happens. Because when the heart beats faster, the blood pressure is going to go up. If our blood pressure drops for whatever reason, the baroreceptors are going to detect that. And their response there is going to increase the cardiac output. It's going to increase the resistance to bring the blood pressure back up. a patient that has a laceration on an artery and they're bleeding out here, they're going to be losing blood volume. They're going to be losing blood volume, and that's going to cause the heart will respond to that drop in blood volume by increasing the heart rate. Because if you lose, it sounds counterintuitive. Why is it going to beat faster? Because if you're losing blood volume, your blood pressure is going to drop. You're going to have less blood. And the heart will respond by beating faster. It has less blood to pump, so it's going to try and pump it at a faster rate. It's going to try and maintain the same amount of blood flow to the tissues and the organs by beating faster. The heart doesn't know that there's a laceration and you're losing blood. So when you have an injury where we're having blood loss, it's not unusual for the heart rate to go up to try and compensate for that blood loss. It's trying to send the same amount of blood out to the tissues that was going before when you were pumping at a normal rate. And so you will see constriction of blood vessels to raise blood pressure. Because blood vessels don't know why. The blood pressure is dropping, so you're going to constrict the peripheral blood vessels. The heart's going to be beating faster to try and compensate for that blood loss. It's going to compensate for the drop in blood pressure. The baroreceptors will detect the drop in pressure and say, hey, beat faster. Vasoconstrict and beat faster. Try and make up for it. But the unfortunate side of that with an injury is that if the heart's beating faster, you're going to be losing blood at a faster rate, which is going to cause the heart to beat even faster. And if the blood loss is uncontrolled, then it all comes to a bad end. Okay. And I've said this several times already. The pressure receptors, the pressure receptors are located in the carotid sinus and the aortic arch. We also monitor oxygen and CO2 levels here. There are chemical receptors located in the same location in the aortic arch and the carotid sinus that are going to monitor for CO2 and monitor for oxygen. Our CO2 levels are we imply those based on pH. It's a whole lot easier to measure pH in the blood than it is to try and determine the CO2 levels throughout the body at different locations, but pH is pretty consistent. So, and so we regulate then chemical changes, physiological changes, blood loss, whatever. We can control this primarily through the medulla. The medulla is going to detect all these changes from pressure receptors and from chemoreceptors in our body, and it will respond. If blood volume drops, causing a drop in blood pressure, the heart rate will go up. Vasoconstriction will occur. If the blood pressure goes up, we will reduce the heart rate and we will dilate the vessels to bring the blood pressure back down. These are all short-term fixes. We do this all the time. We're constantly going through this vasoconstriction, vasodilation, heart rate up, heart rate down as we do things in our daily activities. Walk up a flight of stairs, run up a flight of stairs, walk out to the car, run out to the car, cut the grass, swim, play sports, whatever, or just sit and read, sit and watch TV, or sit and game, whatever you do, different things are going to require different responses. Now, hormonally, we use hormones from the adrenal medulla, epinephrine and norepinephrine, our fight or flight hormones. That will cause an immediate change in blood pressure. We will have, epinephrine and norepinephrine causes a rise in the heart. Epinephrine causes an increase in the heart rate. Norepinephrine causes vasoconstriction, so our blood pressure goes up. That's what we expect to see in a fight or flight response. We shut down the flow to the unessential organ systems temporarily, or at least minimize the flow. You don't block off flow completely. We minimize the flow. And we respond then in whatever kind of fight or flight stress we have. So, and it's designed to protect us. And we've all experienced a fight or flight moment at some point. Somebody, you're in the car and someone almost hits you, and you respond very quickly, and maybe you steer out of the way, or somebody runs in front of you and you step on the brakes quickly, or you're in an accident. Somebody hit you, you're in an accident, and your response is the fight or flight, the adrenal medulla kicks in, and you have all this surge of epinephrine and norepinephrine, and then afterwards you're tired, you're cold, it takes a long time, and it takes a long time for the epinephrine and norepinephrine to wear off. Now, ANP, atrial natriuretic peptide, which is why I like to say ANP. This hormone released by the atria, and we talked about this in the endocrine chapter, tells us to secrete sodium. Sodium's key. ANP, if it detects a rise in blood pressure. Now, the atria are going to get enlarged if there's more blood coming into them. So their response is going to be, hey, if we have more blood coming in, there's more pressure in the atria. The first thing they'll want to do is cause our bodies to excrete sodium in the kidneys. It's going to come out of the distal tubule. We'll talk about that in lecture. So they do this. How they control sodium is by reducing the effect of aldosterone and renin-angiotensin secretions. It's by simply inhibiting the renin-angiotensin-aldosterone sequence. Remember, the aldosterone causes us to retain sodium. When we retain sodium, we retain water. And when we retain water, our blood volume goes up because all water ends up in our blood. And when our blood volume goes up, our blood pressure goes up. So to counteract this, ANP interferes with the renin-angiotensin-aldosterone mechanism, so we don't retain sodium. We actually get rid of sodium. When we get rid of sodium, we get rid of water. So the more sodium that we excrete, the more water is going to go with it. Our blood volume goes down and our blood pressure goes down. Antidiuretic hormone. If our blood pressure drops, another thing antidiuretic hormone does, it can function as a vasoconstrictor. So if our blood pressure drops, antidiuretic hormone will cause our blood vessels to constrict. If our and when we they're a very powerful vasoconstrictor, and when ADH is released, then we will constrict vessels. If our blood pressure is dropping, it will constrict blood vessels and raise our blood pressure. It will also tell us to retain more water, because that's what antidiuretic hormone means. It retains more water, which increases fluid volume in the blood, raising our blood pressure there. And even angiotensin 2, in the renin-angiotensin-aldosterone sequence, angiotensin 2 is also a vasoconstrictor. So before we ever get to aldosterone, we have a short-term vasoconstriction effect. We will constrict our blood vessels before angiotensin 2 triggers aldosterone and telling us to retain sodium and retain water and increasing blood volume and increase blood pressure. That was a mouthful. Angiotensin 2 alone will cause vasoconstriction before it gets to that next step. So when we're doing the renin-angiotensin-aldosterone, we're going to vasoconstrict and start the increased pressure, and then we're going to end up with the aldosterone, sodium and water sequence. So And ANP will interfere with all of that. So you have 4 different hormones here that are going to affect our blood pressure. The epinephrine and norepinephrine will cause a rise in blood pressure and heart rate. And vasoconstriction and heart rate increase gives us an increase in blood pressure. ANP will lower our blood volume, lower our blood pressure. ADH will raise our blood volume, and angiotensin II will raise our blood pressure. So, other chemicals. Nicotine is a vasoconstrictor. A person that smokes will, the nicotine in tobacco smoke will cause vasoconstriction. There are nicotine receptors on the blood vessels. There are nicotine receptors that on the autonomic nervous system responds to and triggers vasoconstriction of the smooth muscle surrounding our vessels. So a person, they light up a cigarette, it will trigger an increase in their blood pressure. Nitric oxide, on the other hand, is a very, very powerful vasodilator. And we release nitric oxide all the time to keep our blood vessels dilated slightly and to make them non-sticky for platelets. But we can release large doses of nitric oxide to cause vasodilation. A person who is having chest pains, a condition known as angina, because these chest pains are being caused, they're not having a heart attack, a myocardial infarction, they are having muscle tissue in the heart being slightly deprived of oxygen. That causes pain. So the treatment for that is a nitroglycerin tablet dissolved under the tongue, releasing nitric oxide in the body, and causes a systemic wide vasodilation, not just the heart, but everywhere. So nitric oxide, that's its primary job. So vasodilator. Histamine is a vasodilator. That's why our nose runs when we're exposed to pollen. Pollen activates histamine receptors, and we release histamine to try and flush the irritant away. Our vessels become leaky, and we lose interstitial fluid, and we call it mucus when it's leaking out our nose to try and wash away the irritant. So it's also part of what we call the inflammatory response. The inflammatory response is our way of dealing with infections and injuries. When we have an injury and an infection, we increase the release of histamine to increase to vasodilate the vessels leading to the site of the injury, and to allow those vessels to become leaky, so that the white cells have a mechanism for getting out into the tissues and destroying, damaged or infected tissue. Alcohol is also going to cause vasodilation. Alcohol inhibits antidiuretic hormone. We've said this several times. When you drink alcohol, and you have to pee a lot, because ADH isn't there to restrict that natural antidiuretic. Alcohol interferes with the release of antidiuretic hormone because it depresses the vasomotor center in the medulla. So we don't release antidiuretic hormone. Our blood vessels dilate, and of course we also pee a lot too. We vasodilate in our skin. Now, we may, why some people that have had a lot to drink, their skin appears very flushed. So the blood pressure drops. The skin becomes, it can also become desensitized to touch too, as the blood pressure drops. So antidiuretic hormone also, causing this, we're blocking antidiuretic hormone is a vasoconstrictor, but alcohol inhibits that. And so your vessels dilate, and since you're interfering with the vasoconstrictive properties of ADH, and you also pee a lot. And if you pee a lot, you're going to reduce your blood volume, which drops your blood pressure. Long-term mechanisms. We control this in the kidneys. The kidneys are going to affect long-term blood pressure control. The long-term control in the kidneys, and this is sort of how it sneaks up on us over time. We change our blood volume. We get used to retaining more water or losing more water. You know, it works both ways. We can go either way on this. We can have increased blood volume with increased pressure. We can lose water and have less pressure. If our blood pressure goes up, the kidneys will typically remove more water. The way they do that is by when the kidneys excrete more salt, they will excrete water. So when kidneys excrete salt, they're going to excrete water. And that's going to lower the blood volume, which lowers our blood pressure. So the kidneys work long-term to fix it. If we have a long-term, if there's a rise in blood pressure, our kidneys are working hard to try and lower that by getting rid of salt, which gets rid of water. Now, salt here is key. You have a patient with hypertension. What do you typically recommend they not eat? Salt. Because the person who eats salt, adds additional salt to their food, will also end up retaining more water. That water increases their blood volume, raising their blood pressure. What the kidneys want to do to lower blood pressure is remove salt and remove water, because water will follow the salt. If the pressure has dropped, then the kidneys will retain water by retaining sodium. So this is long-term control of the kidneys. The kidneys, blood pressure up, we get rid of water. Get rid of water. Where's water located? Water's in the blood. If we decrease blood volume, blood pressure goes down. You get rid of water by getting rid of salt first. If our pressure's down, we raise it by increasing fluid volume of the blood by retaining water, by retaining sodium. So kidneys can do this directly and indirectly. There's two mechanisms in here. The direct mechanism, pee out the water or retain the water. If we get rid of sodium, we're going to get rid of water. Our blood volume drops and blood pressure goes down. If our blood pressure is low, we want it raised to go up. We are going to retain sodium, which allows us to retain water. Remember that water always follows sodium. If sodium drops, water will drop. If sodium rises, water will rise. So if the water goes up, blood volume goes up, because all water ends up in the blood. So if we retain salt, we retain water, we increase blood volume, blood pressure goes up. If we get rid of salt and we get rid of water, then our blood volume is going to drop and our blood pressure will go down. Those are the direct mechanisms. All depends on the presence of salt and water. The indirect mechanism is our old friend here, renin, angiotensin, aldosterone. So, and if our blood pressure, it's a very nice, busy little chart there. But basically what happens, if our blood pressure drops, then the kidneys will detect that. And the kidneys will secrete renin. Renin activates angiotensin 1, and angiotensin 1 is converted to angiotensin 2. And angiotensin 2 is a vasoconstrictor on its own, which causes the constriction of our vessels to begin with. Then it will stimulate the release of aldosterone. Aldosterone tells us to retain sodium. And when we retain sodium, what did I just say? If we retain sodium, we retain water. If we retain water, our blood volume goes up and our blood pressure goes up. And that is our indirect mechanism by using renin, angiotensin, aldosterone. We don't have to use the indirect mechanism That's not the first choice. The first choice is always for the kidneys to either retain sodium or get rid of sodium. Get rid of sodium, water follows it, blood pressure drops. Retain sodium, water follows it, blood pressure goes up. But here, the indirect mechanism involves the more elegant renin angiotensin 1, angiotensin 2, aldosterone sequence. Okay, I have 11:23. So this is probably a great place to stop. We'll pick up with this tomorrow. Remember that tomorrow, I'll send out an email to remind everybody, we are not starting until 10:30 because I have to do a demonstration in Sevierville on the anatomage table that I've gotten roped into. I didn't say that. So we will go from 10:30 to 12:30 tomorrow, and we'll finish this chapter and we'll start moving into the heart. I'm really trying to save the heart discussion until we get into lecture on Monday. So, but I will post this video for you. Of course, there's no lab this afternoon. You should have seen I posted all the videos from yesterday, last night. If you have any questions, shoot me an email. I'll be happy to answer that. If anybody has any questions now, I'm happy to answer that. In that case, if not, I'm going to stop the sharing and I'm going to get us out of here. And I will see all of you tomorrow at 10:30. So, like I said, see you later. Okay.